All right, we have a quiz when we get together on Sunday. And if you look back over the course schedule, you'll notice that the coverage for the quiz is since the last time we had a quiz. So that means that classes 16 through 22, which is today's lecture, all that information is fair game for the quiz. Now, there will only be one question on the quiz, and so you can't expect that you'll get something covering everything, but I haven't written it yet, so I don't know what the topic will be. And I probably wouldn't say exactly what it was going to be even if I had written it yet, so I guess you'll just have to remain guessing. Looking at a week from today, then homework 6A is due. In Chapter 6, we start talking about momentum, and that's the subject of today's lecture. Now we're in Chapter 6, which is momentum. Any questions before we go? All right. There is a video I want to show you about momentum. So let's watch this. I think the audio works on these speakers, if I'm not mistaken. Ooh. Panel's falling off. It's high quality equipment. This is a video that I've been showing students for a long time. It was taken in Finland. Let me dim the lights. Maybe these speakers don't work. Let me pause it for just one moment, and if we can't get the audio working, then I'll just tell you what he's saying. No, there's no sound. All right, so what we're looking at are boots with a rocket attached to it. And it's not necessarily a rocket. A rocket is different from a jet. A rocket is when it's a solid propellant that's burning and it's inside of a casing. This is actually, there's some fuel in the bottle there. He's burning kerosene, and I guess that's the highest quality. It's burning kerosene, and it takes air in through the boots. He's testing the boots right now, just making sure that they work, and what he's going to do is take a balloon once he warms up the boots, because this is during winter in Finland, which is pretty far north. It gets very, very cold in Finland. And those are the fuel tanks. Of course, it's a completely safe thing to be stuffing liquid kerosene into your flight suit there. And what he has on is one of those wingsuits, the kind where you can get a little bit of forward motion when you jump down. You can't fly level normally with the wingsuit because you're dropping. But with rocket boots, he's hoping to maintain some level flight. Sitting on the edge of a platform. I don't remember the starting elevation. It says in some statistics I've got in a moment. Seems a little bit brave, or maybe reckless, to be sitting on the edge of a hot air balloon with a bunch of fuel stuffed down your suit. He didn't hesitate. And then he sort of flies away. The person who doesn't have on the wings, the boots, is falling down, and he's maintaining elevation, and in fact is able to climb just a little bit by having those jet boots on. And so this is an illustration of momentum. The fuel that is inside the bodysuit there is burning and creating a really fast exit velocity, and then he was able to achieve forward flight. So let's look at some statistics here about this situation. Okay. All right, so those boots, oh, I better actually, okay. Those boots generate 16 kilograms of thrust each, and there's 2 of them. And to warm up the engine before it actually starts its normal operation, he has to prime it with a mixture of butane and propane. And the reason for that is that butane and propane are gases, and it makes it easier for them to get the jet going. Those are the same kind of like jets that sometimes model enthusiasts would put into little model airplanes, and this guy instead strapped into his legs. It uses 0.5 liters of fuel per minute, And so I think that each one of those blue flasks that he was holding was a liter each. And so I think he had enough fuel for up to 2 minutes of flight. And it was 7,000 feet, so I don't know, in terms of meters, that's roughly like 2,000 meters that he's jumping from, maybe 2,400 meters. And he was able to achieve horizontal flight, but then when he tried to get some additional elevation, began to start stalling. So pretty interesting situation of turning fuel, it's this kerosene, into forward motion. Now, I'm sure that many of you have taken some principles of momentum in your physics class before. In previous physics classes, you maybe remember that momentum is mass times velocity. And so what we're going to do today is talk about how momentum as applied to fluids is derived. And it starts with Newton's second law, which says the sum of the forces applied to some sort of a body are equal to the mass times acceleration. So if there's an imbalance of forces, a net force in any one direction, then that will cause a certain mass to accelerate. And if we look at the units, mass, of course, is units of kilograms. Acceleration is meters per second squared, and so that's where the newtons comes from in force. A newton is a kilogram meter per second squared. So what we're going to do in momentum as a first step of understanding what it is substitute in, instead of acceleration, we know that acceleration is dv dt. So it's the change in velocity with respect to time. And that tells you that it's local acceleration that we're dealing with in momentum. Remember that there's a couple of different kinds of acceleration we've talked about so far this semester. There's the centripetal acceleration, or in other words, rotational flow. There is convective acceleration, which is flow going through a nozzle, and so its velocity is changing as a function of position. But this is local acceleration, which is that classical, it's a body speeding up over time. And so think about if a stream of water has a change in velocity over time. And velocity is a vector. And just to refresh your memory, what that means, the difference between a vector and a scalar only has magnitude, but a vector has both magnitude and also direction. And so part of what we're going to be very careful with here in Chapter 6 is indicating the direction of velocity. Whether it's to the right or to the left has a huge effect on the calculations that we're doing. And we have to be very careful with the sign convention and with our direction notation. Otherwise, our calculations will go off the rails and crash and burn. So we have to be very particular about how we account for velocity when we're doing this momentum. So the change in velocity with respect to time, and mv is momentum. And so think about, even if a train is moving very slowly, because trains weigh thousands of tons, it takes a lot of force to stop a train. Even though a train is moving slowly, you couldn't just stand in front of a train and start pushing on it and expect it to stop. It's easy for me to stop a bullet as long as it's moving slow, though. So if a bullet is just, if I was tossing a bullet up in the air, I can catch it with my hand, right? Because it doesn't have much velocity. But a bullet has a lot of momentum, even though its mass is low, when it has a high velocity. So you wouldn't want to try and catch a bullet if it's moving 1,000 feet per second, because it would just go right through your hand. So momentum takes into account both of these things, mass and velocity. Okay, so the next step in our development here is substituting in the idea of momentum of a system of particles. And remember, when we were talking about the Reynolds transport theorem, we defined a system as a continually connected body of liquid, or even of a fluid, I guess I should say more generally, because it can include a gas. And so mv is momentum, and what we're saying is don't just think in terms of a single solid object, but even fluids can have momentum as well. A stream of gas that's moving has both mass and velocity, and so it can have momentum. Now you'll remember Reynolds transport theorem, and we said that there were two terms, speaking generally, in Reynolds transport theorem. There is the storage term, and then there's the transport term. And so the first one is storage. It has to deal with the control volume. So here CV is talking about the control volume. And in this term, what we have is v is velocity, and then this density times the change in volume with respect to time. This is our mass term. Remember, we're starting with the idea of mass and velocity. Those are the two components of momentum. So here, in the storage term, there's the velocity, and then density dv dt is the change in mass over time. So it's going to be the change of momentum inside of the control volume. That's how to interpret this first term of the Reynolds transport theorem when we apply the ideas of momentum. The second term is what we call the transport term. And CS is talking about the control surface. And so control surfaces, we're thinking about the flow of momentum across a boundary. The inside of our control surfaces is the control volume. And so here the lowercase v is talking about the velocity. And then previously what we've had in the transport part of the Reynolds transport theorem is the density of the fluid, the velocity of the fluid, and then some incremental area. And so this is the second term, density, velocity, dA. So V times A is the volumetric flow rate, Q. Multiply that by the density, and that gives you the mass flow rate, m dot. So both of these end up having an m dot, the mass flow rate term, both the accumulation and the storage. The thing is what we're going to eventually see is it's pretty unusual to have an accumulation of momentum. There are some devices that can do that can accumulate momentum, for instance, a flywheel. But in the types of problems we're going to be solving, we won't normally have to deal with this first term, which is the storage of momentum in the control volume. But if we just combine all these ideas together, starting with Newton's second law, we're going to say that the sum of the forces applied to a body. So how we're usually going to interpret this left-hand side of the equation is with the phrase I'll write on the board here. It is the forces required to, and anytime I write on the board, you might want to write it down as well. The forces required to hold the system steady. This is going to be really important in understanding what kind of a force you calculate, because it can either be these momentum problems, it can tell you the force that the fluid is applying to an object, or the force you have to apply to hold the object steady. And so those are equal and opposite reactions. And so the notation here, sum of F, the way we solve our problems, what we'll be solving for is the forces required to hold the system steady. So to keep it in equilibrium. So there's two parts to momentum. There's the accumulation of momentum in the control volume and the flow of momentum through control surfaces. Most of the time, we won't have momentum accumulation. Let me just draw a little example on the board here. If we had a steel part that had pieces like this, if there was a jet of water that was going this way, and it started to spin around in a circle, then that would be the accumulation of momentum. If we drew an imaginary boundary across this, and some of the jet's coming out now, if we stopped the jet, it would continue spinning. And so there can be an accumulation of momentum inside of a control volume, but it's pretty unusual to try and store that momentum for the types of vanes, jets, and cut pipe sections like we're going to be solving in Chapter 6. So what we're saying here is let's simplify the Reynolds transport theorem to say that there's no accumulation and that we have steady flow. So steady flow means that conditions are not changing over time. And so what that does is it simplifies our relationship here to the forces required to hold the system steady are the difference between the in and the out of the velocity coming through the control surfaces. So let's talk about what I mean by forces. There's different types of forces, for example, gravitational, electrostatic, and magnetic. those body forces don't actually have to come into physical contact with an object to act on it. But the other kind of forces that we're actually going to be dealing with are surface forces. And surface forces do require a physical contact. And so an example of a surface force would be a hydrostatic force, where you have water pressing on a dam. And the physical contact between the fluid and a solid object requires a force to resist the hydrostatic force, and we're also going to be talking about forces required to resist momentum. So this is what you're actually going to use for problem solving. And I'm going to provide an equation sheet for the second exam, and this is what the equation sheet version of the formula is going to look like. You can apply the momentum expression in many different directions. Here I'm just saying let's consider the forces in the x direction and the velocity and the flow in the x direction. So what it says is, on the left-hand side, the force required to hold the system steady is the sum of the flow through the control surfaces out minus the sum of the flow through the control surfaces in. So here we have something coming into the control surface and going out of the control surface. Let's simplify it even more and just have this stream only in the x direction. Here is our control surface. I'll draw the little dashed lines to illustrate that it's kind of just an imaginary line. We've got a jet coming in and a jet going out, a stream of water. And so what we need to know is the mass flow rate of the in, the mass flow rate of the out, and then the component of the velocity in the x direction, out and in. Now here, if it's horizontal, then all of the jet is in the x direction. But it's not always the case that we have jets going only exclusively in the x direction or in the y direction. So we can also apply this equation in y or z. So here all that changes when you consider the sum of the forces in the y direction. The mass flow term isn't relative to x or y, but the velocity is, because mass flow is a scalar, meaning it only has magnitude but not direction. But then the velocity is a vector, so we do have to consider the component of velocity that's in the direction we're interested in. So as I said before, the sign convention is really important. If you mix up the flow in and the flow out, you put them in the wrong place in this formula, you're going to get the wrong answer. And likewise, if you mix up to the right is positive in the x direction versus to the left should be negative, then you're also going to get the wrong answers there. So what I say is, let's assume that when we're talking about the x direction, to the right is a positive velocity and to the left is a negative velocity. And then when we're in the vertical, up is positive and down is negative velocity. So those are the sign conventions that we're going to be using for momentum. And so it should be obvious. If you have a control surface, you've got a flow in through a boundary, a flow out through a boundary. And so when you're substituting into the terms here, it's a little confusing to have the out term first, and we're subtracting the in term. But that's just the way that it works when we want to solve for the force required to hold the system steady. So, for instance, here, in and out, the outflow is positive x because it's to the right, and the inflow term is positive x because it's to the right. Okay, this one, what you can sometimes have is you can have two streams coming in, and inside of the control volume there would be some sort of a vein or a pipe network that's redirecting the flow so that it exits in a different direction. And so here we have two streams coming in and one stream exiting. So you'll notice that the stream out is in the y direction and it's negative y because it's down. The first stream is to the right, so we'd give that velocity the positive sign. And the second stream is to the left, so we'd give that velocity a negative sign. Okay, so let me ask you this. Write on your notes, in the same way that I've been doing this, velocity out is positive, velocity in is positive, and so on. Classify these three streams. Each one of them has an x component and a y component, and each one of them is either in or out. So get some practice classifying those three terms using the same kind of notation that I've just shown you for these first two examples. Just like the x component and the y component. Eventually will, but I'm just asking, is it positive or is it negative? Yeah. Okay, so stream one, is it an in or an out? It's in. It's a flow in. And so the way that we'd write it is we'd say the velocity in. Now what about the x component? In the x component, is it positive or negative? That's right. So it's to the right, so it's positive. What about the velocity in the y direction? Negative, right? Okay, so stream two, in or out? It's also an in to the control volume. Velocity in the x direction? Negative, because it's to the left, right? So negative. Velocity in to the y direction? Also negative, because it's downward component. Okay, stream three, out. Velocity in the x direction? Oh, there's no in, right? So there's no velocity in the x direction. It's velocity out in the x direction. It's positive. What about the velocity out in the y direction? Also positive. All right. So if you're careful, you'll never make a mistake because it's easy. So when does the problem come? It's when you're hurrying or when you don't take the time to actually write the detailed note to yourself. So here's our problem-solving approach. What we'll do when we have problems like this is we're going to begin by putting together a sketch, trying to make a drawing that sort of illustrates the problem. And we're going to identify governing equations. So what that means is that sometimes we're going to combine problems together. Like you remember on this assignment that you've just turned in that sometimes you'll have Bernoulli's equation and the the continuity equation. Or sometimes you'll combine the ideas of, let's see, another one that we did combined was the manometer equation along with Bernoulli's and continuity. So we're going to do the same thing here where it's not always just momentum by itself, but sometimes it's going to be other formulas coming together as well. Drawing the forces that apply are going to help you to sort of know the direction, like instinctively, before you start doing the calculation so you can check your work to make sure that it makes sense. Like if you know that you would have to push to the left to hold something steady, then at the end of your calculations you better find that the x direction is negative and so on. So I'll really emphasize us doing drawings when we can to make it clear what the directions are. All right, so here we have an example of a balloon. And from the picture, we're holding this balloon steady by pushing to the left direction with this external force. If this external force wasn't applied, then the balloon would start sliding to the right. It would start to move. What we know is the pressure inside the balloon is given as 0.4 meters of water. And this is a way of measuring pressure that we haven't talked about very much before, but what it means is that the pressure of the air inside the balloon is the same pressure that you would have if you were 0.4 meters underwater. Sometimes atmospheric pressure is, the barometric pressure is often described in terms of millimeters of mercury. And this is the same kind of an idea. This is a depth of some fluid as a way of describing a pressure. We've got the diameter of the opening of the balloon is 1 centimeter, and then we know the density of the air. Okay, so I've told you that basically the solution outline here is to start with Bernoulli's equation and find the velocity of the gas as it exits the balloon. And the continuity relationship stuff that you've been working on recently will help you to find the exit velocity. And then you apply a momentum equation to find the force required to hold the system steady. So we've got plenty of time. I'd like you to give this one a crack. And starting with Bernoulli's equation, find out how fast the air is exiting the balloon. And then, once you know the exit velocity, apply it to the momentum equation to find out what's the magnitude of that force required to hold the system steady. Okay, let's double check the first part of this problem to make sure that we're all on the same page. All right, so we have a balloon where there is a pressurized gas on the inside, and then that pressurized gas is escaping through the opening, and then there's a stream of gas going out. And it's that stream of gas exiting that causes the force of the balloon that, if we didn't resist the balloon, then it would start moving. Okay, so what we need to do is find out, first of all, the velocity of the gas as it escapes. And here's some of the preliminary stuff. We can calculate the area of the opening because we know the diameter is 1 centimeter. So here's the area of the opening in terms of square meters. And then the pressure was given in this unusual 0.4 meters of water terms. And that's not anything too confusing. It's just that's the same pressure as you would have if you were 0.4 meters underwater. And so we're multiplying, using the hydrostatic equation, the depth of 0.4 meters, multiplying that by the unit weight of the water. And so the pressure at the center of the balloon is 3924 newtons per meter squared. That pressure is pretty high. This example is maybe a little unrealistic because I don't know if a balloon could have that much pressure. But it's just to illustrate the formulas, really. All right, so any questions so far on these preliminary calculations? So it's Bernoulli's equation that allows us to calculate the velocity of the exit gas. What we're saying is that assume that we're working along a streamline for steady flow and that the gas is inviscid, and so it's also incompressible. Bernoulli's equation is an okay assumption for this case. The gas is under some pressure at 1 and it's not at 2, but we're just going to use it to estimate the velocity of the gas going out. Now the velocity is to the left. And I guess to be strictly correct about this, I should have written that the velocity is negative 80.87, because here in Chapter 6 it's really important for us to be considering the direction of the exit velocity. And this is a flow out, not a flow in. So it's to the left.
So even if the answer is positive, we need to put the negative sign. So we can that safe.
So the way that you can express the directionality of this velocity is you can either say the magnitude of it, and then in parentheses maybe you could say to the left, just to emphasize that and to remind yourself that it's also the direction that's important in addition to the magnitude. Here, since I've got a drawing that shows the velocity is to the left, then that's another way of indicating that you know what the velocity's direction is because here I've got the arrow pointing to the left that's showing the direction of the stream of gas as it exits the balloon. All right, so then the momentum part of it. Here's the momentum equation. Has anyone got this far yet? Actually, I remember seeing a couple of people had the right answer all the way. So let me give you a word of caution. If we expand out the term for mass flow, so there's no in here. We can cancel out the whole last term. There's only flow out. What is mass flow rate? What's the formula for that? Okay, density A times V, right? So that's mass flow. So here we've got mass flow and then velocity. Sometimes students are tempted to make a simplification and then it ruins the problem for them. Ordinarily it'd be fine, but sometimes the simplification that they're making is they're saying density, area, velocity, and then here you've got a velocity. So sometimes what they'll do is they will just square that. Why do you suppose that could be problematic? That's right. Okay. So mass flow is a scalar. So it's not going to be affected. It's not going to be negative or positive. It's just going to be some amount. But then the velocity here, sometimes it'll be positive, sometimes it'll be negative. If you square the velocities, then all of a sudden, even if it's negative, this result will always be a positive amount. And so you need to keep it separate. Even though there's a velocity in the mass flow term, and then a velocity after the mass flow term, keep those two velocities separate because you want to have a negative of the entire, the product of those two terms should be negative if it's a velocity to the left, like it is here. So in the calculations, you'll notice I first calculated the mass flow. So I have the density of the gas, the cross-sectional area of that opening that the gas is going through, and then the velocity of the gas. So mass flow will be kilograms per second. And then I've got the negative sign here because the velocity is to the left. And so the velocity is going to be the force, negative 0.616. And then below that I've written what this means. It's the external force required to hold the system steady. So if we don't apply this force, then the balloon is going to start to move to the right. All right, so are there questions from this approach? I told you that the second exam isn't going to have a lot of equations on the equation sheet. Basically we're using one equation for all of Chapter 6. We had basically one equation for all of Chapter 5. It was the continuity equation, Q equals VA, right? That was the main idea of the whole chapter. And then we only have, I think, 4 formulas really in Chapter 4. There's Euler's, Bernoulli's, rotational flow, convective acceleration definition. So it's a short formula sheet for the second exam, but these are really powerful ideas, and we can combine ideas together to solve some pretty complicated problems. All right, so any questions as we wrap up from this example? So what should you be doing in the course? Just as a reminder, what you should be doing. We have a quiz on Sunday and then a homework assignment due on Tuesday. Why don't you take a look at these problems? I think some of them you can already get an early start on, and just by looking at the others, you'll be sort of in the right mindset for the lecture that we have next Sunday. So I'll see you then, and have a great day.